Hello, today I will be talking about how to calculate the electrical field of a uniform ring of charge. The reason why this problem is interesting is the entire ring has a uniform charge, and if you pick any point in space and try to calculate how the charge from the ring affects it, you'll find that because the points on the ring are at different angles and distances from any point in space from one another, that you will see some interesting effects. This problem you will find in a electromagnetic physics course and in real life too. So let us break this down. So we have this ring here, and it's uniformly filled with protons, and the reason why we pick protons is because of the math. Using a positive charge is slightly easier than using a negative charge. So if we say that this is a uniform circular ring with radius A from its center, and the point we want to evaluate is not on or in the ring itself, but a point P right here, which we can say is a distance away. Terrible at lines. It is a distance of x from the center, and the line x is a bisecting axis perpendicular to the ring itself. So one thing to know about this problem is because this point P is receiving an electrical field from every single infinitesimally small point on the ring, you're going to be receiving fields at different distances and different angles. Because this ring is a circle, the problem is slightly easier, but if this was, say, an ellipse, that's when the calculus would be fun. So the whole purpose of using electrical fields from uniform shapes is to be able to use calculus to break up these shapes. So for example, if we break up this ring right here into infinitely small pieces of charge along its surface, say right here, and we call those charges dq, because q usually denotes charge and the d from calculus means a very small point or a very small piece that you will put together in an integral or a derivative. You can do the opposite. So if we look at this infinitely small piece of charge on the ring dq and just look at the properties of this point, we can use calculus to find out the effects from the entire ring itself on point P. So if point P right here is x distance away on this axis, then we need to create an axis from our infinitely small piece of charge right here dq to point P. So let us make an axis right here, and we'll say that the angle between this axis, which we can say is r, and x, the angle we can call theta. So we want to find out the electrical fields coming from dq onto point P. So what we can do is, because we know that the ring has a uniform positive charge, the electrical field vector coming off of any point of this ring will be pointing away in a straight line from that point on the ring in terms of point P. So for example, from dq to point P, the electrical field vector goes this way. Goes this way. This is the electrical field vector. But in terms of point P, we don't need this entire vector. The reason is, for every point on this uniform ring, there is an opposite point that cancels out the vertical component of that vector. So for example, for dq, down here we have this infinitely small point of charge, that if we draw its vector, you can see that this part and this part will cancel out, but they both have this horizontal part, which will add together, so we need to look at the horizontal part. Plus, in terms of this bisecting axis x, we want to look at the electrical field on this axis, which agrees with the vector addition. So we can ignore the vertical components of the electrical field vector. So now mathematically, we need to break up that vector and analyze it. So if we break up this electrical field vector right here into the vertical part, which I said we don't need to care about because it will cancel out with another point's electrical component, vertical component. We just look at this x part. This is the horizontal component of the electrical field vector. So we need to relate this electrical field vector to that horizontal component. Also, one thing to notice is because this electrical field vector is coming from the infinitely small part dq and not the entire ring itself, this is just going to be a part of the electrical field in total, so we can call that dE. So we need to mathematically relate dE, and this will be dE in the x direction because the electrical field that matters is in the x direction. So if we just use trigonometry, we can relate the two by saying dE in the x direction, the electrical field vector in the x direction, is just going to be simply equal to dE times the force vector itself times cosine of theta, right? The reason is, if this is our dE vector, and this is theta just from that triangle, and this is dEx, mathematically we can just convert dEx to dEx from dE with a cosine of theta. So that's just throwing in the cosine of theta. Now the problem with this is theta is another variable. Because if this wasn't perfectly uniformly circular, the angle theta would change depending on which point you chose. If you chose right here, theta would be different than if you chose right here. So we need to find a way to convert cosine of theta into an expression using variables that won't change. And two variables that won't change, or three, will be this distance, x, from point P, the distance r from point P, and the radius, because this radius will stay the same because this is a uniform circular ring. So we can convert cosine of theta, looking at this triangle here, to adjacent over hypotenuse, so x over r, so that will equal cosine of theta. And we can break this up even more because r is just going to be the square root of x squared plus a squared. So now cosine of theta will equal x over the square root of x squared plus a squared. So this is our cosine of theta. So now if we plug that back into our equation for dE in the x direction, we see that dE in the x direction is equal to dE vector times x over the square root of x squared plus a squared. Okay, now we need to substitute an expression in for the differentiating electrical field, which you can just take from using this differential equation for the electrical field is equal to k, which is 9 times 10 to the 9th power, times the changing charge over r squared. This is just taking kq over r squared and differentiating both sides. So if we plug this part in for dE, we can simplify this expression even more. So now dE in the x direction will equal k times dq over r squared, which is just dE vector, times our cosine theta, because this is still in the x direction, and our cosine theta was x over square root of x squared plus a squared. Okay. Now what we can do is plug, using the same Pythagorean theorem we used right here to convert r into square root of x squared plus a squared, we can convert this r with Pythagorean theorem. So if r equals the square root of x squared plus a squared, then that r squared will just equal x squared plus a squared. So now this equals k dq. That's a terrible line. So k dq over x squared plus a squared multiplied by x over square root x squared plus a squared. And all this is equal to the differentiating electrical field vector in the x direction. So now what we can actually do is combine the denominators. So this down here is to the first power, right? And this is to the 1/2 power because it's in the square root. So we can combine those by adding the powers. So 1 plus 1/2, that's 3/2. So now dE in the x direction is equal to your constant times your changing charge times x over x squared plus a squared to the 3/2 power. Okay, now we just want e in the x direction. We just want the total electrical field vector in the x direction. So we need to integrate all of the dq's. So we need to integrate both sides of this equation to get just e to the x. And this is where the calculus comes in because you're dealing with infinitely small pieces. So now if we integrate both sides, we get the integral of dE to the x, all e in the x direction, is going to, well, with respect to q, because it is a charge, or an electrical field vector based on the charge, is going to be equal to the integral of all of this. Okay, so you're just integrating both sides. So this part essentially becomes very simple because you can just look at an integral table. If you did this by yourself without an integral table, you'd have to do trig substitution, which wouldn't be bad, but it could be annoying. So if we pull out all the constants from the integral, we just get the electrical field vector in the x direction is equal to k times the integral of x dq over x squared plus a squared to the 3/2 power. And if you just integrate this, essentially, you can treat a and x as constants, and if you can just use the integral table, and your answer will be the electrical field vector in the x direction, which is for the whole uniform ring, is going to be equal to your constant times x times the total charge of the ring, assuming that x is much greater than a. And you will get kx times your total charge over x squared plus a squared to the 3/2 power. Thank you very much.